Have you ever considered that our universe might not have had a beginning? What if the Big Bang, a concept familiar to us all, was not a singular moment of creation, but just one episode in an unending cycle of cosmic events? Picture our universe's timeline not as a straight line with a beginning and an end, but as a boundless narrative where the final chapter flows directly into the first. While the Big Bang theory is widely accepted as the foundation of modern cosmology, and for good reason, this magnificent framework isn't without its flaws. There are profound conceptual issues that drive physicists to search for other explanations. Among these, the concept of a cyclic universe stands out as the most elegant and possibly the most profound. Together, we'll delve into how this once philosophical notion has emerged as a serious scientific competitor to the Big Bang model. Our investigation will take us through the processes of cosmic death and rebirth, and we will even hunt for faint signatures of a prior universe within the cosmic microwave background radiation that envelops us. But before we venture into these bold alternatives, it is crucial to first appreciate the monumental structure we aim to challenge: the standard cosmological model. It is far more than a simple hypothesis. It stands as one of the most magnificent intellectual achievements in human history. This theory is not founded on mere speculation, but rests upon three formidable pillars of empirical evidence. These distinct lines of irrefutable observation mutually support one another, painting a remarkably consistent and predictably powerful portrait of our cosmic origins. To truly comprehend why scientists are motivated to look for anything else, you must first recognize the sheer elegance and strength of this existing model. Let's rewind to the beginning of the 20th century, a time when the scientific community, including luminaries like Albert Einstein, perceived the universe in a completely different light. The prevailing view was of a static, eternal cosmos that had always been and would forever remain the same. What we now know as galaxies were then termed spiral nebula and believed to be mere components of our own Milky Way. And the notion that the universe itself could possess a history, a story of birth, evolution, and transformation, was considered the domain of philosophy, not serious physics. When Albert Einstein developed his general theory of relativity in 1915, he discovered that its equations pointed toward a dynamic and unstable cosmos, one that should either be expanding or contracting due to its own gravity. This conclusion was so unsettling to him that he inserted a new term, which he called the cosmological constant, for the sole purpose of forcing his model of the universe into a state of static balance. In later years, he would famously refer to this modification as his single greatest blunder. However, science frequently shows us that reality is far more peculiar and captivating than theoretical predictions. The first fissure in the concept of a static universe emerged from the painstaking observations of astronomers. Back in 1912, an American astronomer named Vesto Slipher was analyzing the light spectra from these spiral nebulae when he observed a peculiar phenomenon. Nearly all of them displayed a shift toward the red end of the spectrum, a property we now identify as redshift. However, science frequently shows us that reality is far more peculiar and captivating than theoretical predictions. The first fissure in the concept of a static universe emerged from the painstaking observations of astronomers. Back in 1912, an American astronomer named Vesto Slipher was analyzing the light spectra from these spiral nebulae when he observed a peculiar phenomenon. Nearly all of them displayed a shift toward the red end of the spectrum, a property we now identify as redshift. To understand this, consider the sound of an approaching ambulance siren, which appears to rise in pitch as it comes closer and then drop as it passes. This auditory illusion, known as the Doppler effect, occurs because sound waves bunch up on approach and spread out as they recede. Light behaves in a similar way. Waves from an object moving away from you will stretch out, shifting its color toward the red, longer wavelength end of the spectrum, while an approaching object's light waves compress, shifting it toward the blue. Slipher's finding that almost all observed nebulae were redshifted implied they were receding from us at incredible velocities, though at the time this was just a fascinating puzzle without a clear solution. The true breakthrough occurred in the 1920s thanks to the research of Edwin Hubble and his associate Milton Humason at the Mount Wilson Observatory. Hubble first established that these nebulae were not local gas formations, but were in fact independent and colossal island universes situated at vast distances. He then meticulously catalogued redshift data, charting the distances to these galaxies against the speeds at which they were moving away. In 1929, his published findings revealed an extraordinary correlation. A galaxy's recession speed is directly proportional to its distance from us. This principle, now called Hubble's law, formed the first observational cornerstone of what would become the Big Bang theory. A useful analogy to understand this is to picture a raisin cake baking. The dough represents space, and the raisins are the galaxies. As the cake expands, every raisin observes every other raisin moving away, and the ones that started out farther apart appear to move away faster. The critical point is that the raisins are not traveling through the dough. Rather, the dough is expanding and carrying them along. In the same way, galaxies are not speeding through a void. The very texture of space-time is stretching, pushing them further apart. Hubble's revelation confirmed that we inhabit a universe in a state of expansion. Logically, if the universe is growing larger now, it must have been smaller in the past. By mentally playing this cosmic process in reverse, we are forced to conclude there was a time when all the substance and energy we can see were packed into an incredibly tiny, dense, and hot point. It is this initial moment that we now refer to, with some irony thanks to its detractor Fred Hoyle, as the Big Bang. What's truly amazing is that theorists had reached this very conclusion even before the observational evidence was in place. As far back as 1922, the Soviet mathematician Alexander Friedmann, followed independently in 1927 by the Belgian priest and physicist Georges Lemaitre, determined that the universe must be dynamic. They reached this conclusion by solving Einstein's equations without any artificial modifications. Lemaitre took this idea a step further, proposing that this expansion pointed to an initial, primordial atom from which everything originated, thereby uniting theory and observation to establish the first great pillar of this monumental idea. The second pillar was significantly more difficult to secure, and its discovery remains one of the most compelling tales of scientific investigation and sheer luck. If the nascent universe was a place of incredible heat and density, then it must have been saturated with a blinding light, a plasma of elementary particles. As the cosmos expanded and cooled, this plasma would have eventually chilled enough for protons and electrons to bond, creating the first neutral atoms. This crucial event, which cosmology places at roughly 380,000 years after the Big Bang, is known as the epoch of recombination. Before this point, the universe was entirely opaque. Photons were trapped, constantly scattering off charged particles, much like headlights in a dense fog. But with the formation of neutral atoms, the universe instantly became transparent, finally allowing that primordial light to begin its uninterrupted journey across space. During the 1940s, physicist George Gamow and his team calculated that this ancient radiation should still permeate the cosmos today. They reasoned that after 13.8 billion years of expansion, it would have cooled and its wavelength stretched from visible light into the microwave spectrum. Their calculations predicted that the temperature of this cosmic microwave background radiation would now be only a few degrees above absolute zero, a bold claim that was untestable with the technology of the era. Then, in 1965, two radio astronomers at Bell Labs named Arno Penzias and Robert Wilson were using a new horn antenna built for satellite communications when they ran into a perplexing issue. No matter where they aimed their instrument, they detected a faint but constant background noise, a persistent hiss that corresponded to a temperature of about 3 Kelvin. They checked everything imaginable, recalibrating their equipment, inspecting every connection, and even famously cleaning out pigeon droppings, which they thought might be causing the interference. Despite their efforts, the noise persisted. It came from every direction in the sky, was present day and night, and never changed throughout the year. Out of options, they reached out to a group of physicists at Princeton University, led by Robert Dicke, who, in a stroke of irony, were in the process of building their own radio telescope for the express purpose of finding the very cosmic radiation Gamow had predicted. When the two teams finally spoke, the puzzle pieces fell into place. Penzias and Wilson had accidentally discovered the oldest echo of the universe's creation. This cosmic microwave background radiation, also known as relic radiation, became the second powerful pillar supporting the Big Bang theory, offering what was essentially a snapshot of the infant universe. Subsequent research using satellites like COBE, WMAP, and Planck has provided us with an incredibly detailed map of this radiation, pinpointing its temperature with remarkable accuracy at 2.725 Kelvin. By analyzing the minute fluctuations in this temperature, we have learned more about the universe's first moments than we ever thought possible. However, a third pillar remained, one that is arguably the most precise and conceptually challenging, as it relates to the very makeup of our universe. When you look around, you see that everything is composed of a particular assortment of chemical elements. But where did they originate? Most of the heavier elements, such as carbon, oxygen, and iron, were forged inside stars and later dispersed through the cosmos by supernova explosions. But the lightest elements, hydrogen, helium, and lithium, trace their origins to a different source. The Big Bang theory offers a very specific forecast regarding these elements. In the initial few minutes after the expansion began, the universe was hotter and denser than the core of any star, functioning as a colossal thermonuclear reactor in a process called primordial nucleosynthesis. Physicists were able to calculate with great precision the exact proportions of elements that should have formed in these conditions. Their models indicated that, by mass, the universe should consist of about 75% hydrogen, roughly 25% helium-4, and tiny amounts of deuterium and lithium. This was yet another prediction, made long before astronomers possessed the technology to verify it. The test required finding the most ancient gas clouds or stars in the cosmos, those not yet contaminated by elements from later stellar generations, and measuring the ratio of their light elements. When these measurements finally became possible late in the 20th century, the findings were astounding. The observed quantities of hydrogen, helium, and lithium in the oldest regions of the universe matched the theoretical predictions with breathtaking accuracy. Imagine finding an ancient recipe, calculating the ingredient ratios to 0.001%, and then tasting a soup cooked billions of years ago, only to discover it is a perfect match. It was a staggering triumph. With the third pillar firmly in place, the monument of the Big Bang theory stood complete. So let us consider this structure one last time. Its foundation is the observed expansion of the universe. It is supported by the pervasive cosmic microwave background, and it is crowned by the flawless agreement between predicted and observed abundances of the first elements. Any new theory aiming to replace the Big Bang must not only introduce a novel idea, but also explain these three fundamental observations with equal or greater success. For many decades, the idea seemed entirely out of reach. The Big Bang evolved from a mere hypothesis into the standard model of cosmology, serving as the accepted framework through which we interpret our cosmos. It presents a narrative spanning 13.8 billion years, starting from an intensely hot origin and leading to the cold, dark, star-speckled universe we see today. Unquestionably, this is among the most magnificent narratives that science has ever constructed. However, just like any grand structure, a close inspection reveals several fine yet profound fissures in its apparently flawless foundation. And our exploration into a radically new vision of the universe begins with the study of these cracks. So, we have erected our intellectual monument. It appears solid, its form is well defined, and the story it conveys is deeply persuasive. Yet in scientific inquiry, as with all great quests, appreciating a discovery is merely the initial phase. What must always follow is a phase of critical examination. A dedicated scientist, much like an expert engineer, has a duty not only to appreciate their work, but to relentlessly probe its integrity, looking for structural weaknesses and unseen flaws. As cosmologists began to apply this rigorous scrutiny to the underpinnings of the Big Bang theory, they uncovered a number of deeply unsettling fractures. These are not issues you can simply write off as inaccuracies in measurement. On the contrary, they represent fundamental enigmas, which imply that the very first chapter of our cosmic history is missing some crucial pages. Let us now delve into these puzzles individually. The first issue, and arguably the most profound, is referred to as the horizon problem. This problem is intimately tied to the second major pillar of our theory, the cosmic microwave background radiation. As I mentioned, this radiation serves as a kind of snapshot of the cosmos when it was only about 38,000 years old. And its most remarkable feature is its extraordinary uniformity. The temperature of the cosmic microwave background, arriving from every direction of the sky, is identical to within 1 part in 100,000. On the map of this background radiation, the variation in temperature between the warmest and coolest spots is practically non-existent. The universe at that stage of its existence was astonishingly uniform, resembling the surface of a perfectly still body of water. At first, you might ask, what is so strange about that? Maybe things have always been this uniform. But this is where a foundational principle of physics, the law of causality, enters the picture. No form of information or interaction is capable of moving at a velocity greater than the speed of light, which acts as our universal speed limit. Consequently, any two separate regions in space can only interact and balance their properties, like temperature, if they exist within each other's light horizon. To put it simply, for one region to influence another, light must have had enough time since the beginning of the universe to travel between them. Now, let's apply this concept to the early cosmos. At the age of 380,000 years, the farthest that light could have possibly traveled from the moment of the Big Bang was, correspondingly, 380,000 light-years. This distance defined the size of the horizon at that time, meaning any two locations separated by more than that could not have had any causal connection. They were entirely unaware of each other's existence. Herein, we find the paradox. When we observe two opposite patches of the sky today, for instance toward the constellation Orion and in the exact opposite direction, we are seeing cosmic microwave background radiation, also known as relic radiation, that came from regions separated by roughly 90 million light-years at the moment of recombination. That distance is several hundred times larger than the light horizon was during that era, which means those two areas could never have been in thermal contact. There was no way for them to have exchanged heat to reach a balanced temperature. To illustrate just how bizarre this is, let's perform a thought experiment. Imagine you are in an immense, pitch-black, and frigid room the size of a continent. At one end, let's say in Lisbon, you put a pot of ice water on a burner. At the far end, in Vladivostok, you do precisely the same. Absolutely no communication exists between these two spots. Yet you find that both pots began to boil and hit a temperature of 100 degrees Celsius at the very same instant, down to 1,000th of a degree. What could possibly account for this? The odds of such a coincidence are effectively zero. The sole sensible inference would be that at some point in the past, both pots were situated right next to each other, their temperatures equalized, and then some unknown force propelled them apart at a tremendous speed. The standard Big Bang model provides no such mechanism. It merely asserts that the universe was simply born with this staggering uniformity. This isn't an explanation at all. It's the assertion of a miracle. And that represents the first major crack in the foundation. The second problem is just as fundamental and is referred to as the flatness problem. According to Einstein's general theory of relativity, the presence of matter and energy warps the fabric of spacetime. The universe can possess one of three potential geometries based on the overall density of this matter and energy. If the density exceeds a specific critical threshold, the universe exhibits positive curvature, creating a geometry analogous to the surface of a sphere. In this kind of cosmos, the angles of a triangle sum to more than 180 degrees, and lines that start out parallel will ultimately cross. Such a closed universe would eventually cease its expansion and collapse back on itself in an event cosmologists term the Big Crunch. Conversely, if the density is lower than the critical value, the universe possesses negative curvature, with a geometry that resembles the surface of a saddle. Here, a triangle's angles add up to less than 180 degrees, and parallel lines will always diverge from one another. This type of open universe is fated to expand indefinitely, growing ever colder and more desolate. Finally, a third, razor's edge scenario exists. If the universe's density is precisely equal to the critical density, its curvature is zero, resulting in the flat Euclidean geometry that you and I learned about in school. In a universe where the angles of a triangle always add up to exactly 180 degrees, parallel lines would extend infinitely without ever meeting. While such a cosmos would expand forever, its rate of expansion would gradually slow to a near halt. So, what type of universe do you and I actually inhabit? Astonishingly, modern observations, particularly the high-precision data from the Planck satellite mapping the cosmic microwave background, reveal that our universe's density matches the critical density to within 0.5%. This means our world is, against all odds, remarkably flat. The real puzzle is that this flat state represents a profound, unstable equilibrium. Picture yourself trying to balance a pencil on its finely sharpened point. In theory, it is possible if you achieve perfect vertical alignment. Yet the slightest disturbance, a gentle nudge or a faint breeze, will cause it to topple. Our universe's flatness is akin to balancing on a knife's edge, where even the most minuscule deviation from the ideal critical density at the dawn of time should have been magnified immensely by gravity over the last 13.8 billion years. To put this into perspective with numbers, for the universe's density today to be this close to the critical value, it must have matched the critical density to within 15 decimal places in the first second after the Big Bang. If the density had been just 1/10 quadrillionth higher in that initial moment, the entire cosmos would have already collapsed back on itself. Conversely, had it been that same tiny fraction lower, the universe would have expanded so quickly that gravity never would have had the chance to form stars and galaxies, leaving behind only a thin, diffuse gas. It's as if you launched that pencil into the air 13.8 billion years ago, and it landed on its tip, still perfectly balanced today. This outcome is not merely improbable. It appears completely impossible without some underlying mechanism. Either the initial density was set with an almost unimaginable degree of precision, or some force actively smoothed out the universe during its evolution. The standard model of the Big Bang provides no explanation for this, instead accepting this extraordinary fine-tuning as an unexplainable initial condition. This conundrum represents the second major crack in the theory. Moving on, the third problem is a bit more exotic, stemming from our understanding of particle physics. For a long time, physicists have pursued a theory of everything, aiming to describe all four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces with a single equation. A significant stride toward this goal comes from what are known as Grand Unified Theories, or GUTs. These theories propose that in the extreme energies of the first moments after the Big Bang, the electromagnetic, weak, and strong forces were all merged into a single, unified superforce. As the universe expanded and cooled, it would have undergone a phase transition, much like steam condensing into water. In this transition, the unified superforce fractured into the distinct forces you see today. Here, however, GUTs make a very specific prediction. This process should have created defects in the fabric of space, analogous to the cracks that form in water as it freezes into ice. These theoretical defects are extremely heavy exotic particles known as magnetic monopoles. So, what exactly is a magnetic monopole? You know that every magnet has both a north and a south pole. If you break a magnet in half, you don't get a separate north and south pole. Instead, you get two smaller magnets, each with its own pair of poles. A magnetic monopole, in contrast, is a hypothetical particle that would be an isolated north or south pole all by itself. According to theoretical calculations, these monopoles should have been produced in vast numbers in the early universe. Being exceptionally stable, they ought to have persisted to the present day. In fact, estimates indicate that so many should exist that their combined mass would vastly outweigh all the visible matter in the cosmos. The issue, however, is that after decades of meticulous searching with our most sensitive instruments, we have not found a single one. Their complete absence presents an enormous problem. Where could they all have gone? The absence of this predicted particle is more than just a minor inconvenience. It signifies a direct and profound conflict between our leading cosmological model and our most advanced theories of particle physics. This contradiction marks the third, and deeply troubling, crack in the foundation of our understanding. To recap, we are faced with three fundamental puzzles. There is the horizon problem. Why is the universe so uniform across regions that should never have been in contact? We also have the flatness problem. How did the cosmos end up so perfectly poised on the brink between eternal expansion and eventual collapse? Finally, we have the magnetic monopole problem. What happened to all the relic particles that should have been forged in the primordial inferno? It is critical for you to understand that these issues do not invalidate the Big Bang theory itself. They do not challenge the reality of cosmic expansion, the existence of the cosmic microwave background, or the successful predictions of how light elements were formed. What they do reveal is that the standard narrative, which begins with a singularity and a straightforward expansion, is an incomplete story. The model works flawlessly from the first second of cosmic history onward, but it offers no insight into what occurred in the very first fractions of that second. These three problems are like mysterious fingerprints left at a crime scene, hinting that something incredibly strange and powerful, far beyond our simple picture, took place at the very beginning. By the late 1970s and early 1980s, these puzzles had become a major source of concern for cosmologists. And since science cannot abide such voids in knowledge, this gap prompted the proposal of one of the most audacious and transformative ideas in modern physics, an idea meant to rescue the Big Bang, but which, as you will see, unlocked a Pandora's box of its own. These cosmological puzzles lingered in the air, casting doubt on how complete our understanding of the universe truly was. It became apparent that the Standard Model required a new introductory chapter, a kind of prologue to describe the very first moments of creation. The breakthrough came from the world of particle physics when, in 1980, a young American physicist named Alan Guth was exploring grand unified theories. He had a sudden insight that these theories held a mechanism capable of solving all three cosmic conundrums at once, an idea he named inflation, which was so potent and graceful that it permanently altered the landscape of modern cosmology. So, what exactly is cosmic inflation? At its most fundamental, it's the hypothesis that in the universe's infancy, between roughly 10 to the minus 36th and 10 to the minus 30th power seconds after the Big Bang, the cosmos experienced a phase of astonishingly swift exponential growth. The word swift barely begins to capture the scale of this event, which involved an expansion far exceeding the speed of light. In a fleeting instant, a subatomic region of space, far smaller than a proton, swelled to the size of a grapefruit, or perhaps even larger. A leap in scale you can visualize by imagining a single atom instantly growing to the size of our entire Milky Way galaxy. It is vital to make a key distinction here. As you know that nothing can travel through space faster than light, a foundational principle of Einstein's theory of relativity. However, inflation doesn't actually breach this rule. During this period, it wasn't matter moving through space, but rather the very fabric of space-time that was expanding and stretching. Because general relativity places no speed limit on the expansion of space itself, this event presents no conflict with the fundamental laws of physics. But what could have triggered such an incredible expansion? Alan Guth, along with other physicists like André Linde and Paul Steinhardt, proposed that a special hypothetical scalar field was responsible, which they named the inflaton field. In the moments following the Big Bang, this field existed in a unique state known as a false vacuum, a metastable condition with immense energy density. This false vacuum energy possessed a very unusual quality, negative pressure, which you can think of as a form of gravitational repulsion. Instead of attracting matter, it powerfully pushed space apart, acting as the engine for inflation. This false vacuum state did not last forever. After an infinitesimal fraction of a second, the inflaton field decayed into its true, stable state of zero energy, much like a ball rolling from a hilltop into a valley below. This transition marked the end of inflation, and the vast energy that had been stored in the inflaton field was released. It transformed into the primordial soup of hot particles and radiation that initiated the standard hot phase of the Big Bang, meaning inflation isn't an alternative to the Big Bang, but rather the prequel that established its ideal starting conditions. Now, you can see how this one concept acts like a master key to solve all three of our cosmological mysteries. Let's begin with the horizon problem, which asks why the universe has a uniform temperature. Inflation offers an elegantly straightforward explanation. Before this expansion began, the entirety of our observable universe was confined to a microscopic region so small that it was causally connected. allowing it to reach a state of perfect thermal equilibrium. Every part was in contact, and the temperature evened out completely. Inflation then took this uniform patch and expanded it to astronomical proportions. So the identical temperatures you see at opposite ends of the sky are not a coincidence, but a shared legacy from their common origin. Next is the flatness problem. The question of why our universe is so remarkably close to being geometrically flat. Inflation addresses this perfectly, and a useful analogy is the surface of a balloon. When the balloon is small, its curvature is obvious to an ant crawling on it. But if you inflate that same balloon to the size of Earth, the ant's world will seem almost perfectly flat for miles in every direction. The colossal expansion smooths out any initial curvature. In the same way, inflation expanded spacetime by a factor some estimate to be 10 to the 50th power or more, effectively ironing out any original curve and naturally driving the universe's density to the critical value, which eliminates any need for fine-tuning. Finally, we have the magnetic monopole problem. What happened to all of them? Once again, inflation provides a simple and elegant solution. The magnetic monopoles didn't vanish. They are still out there, but their density has been reduced to a negligible level. If these particles were ever created, it happened just before or at the very beginning of the inflationary period. The subsequent tremendous expansion of space simply spread them out so far and wide that the chances of detecting one in our observable universe today are virtually zero. Consider for a moment that our giant inflating balloon is in a room that initially contained just one mosquito, representing our magnetic monopole. When the room was compact, spotting it was simple. But once that room expands to the scale of our solar system, the mosquito is still in there somewhere. What are your chances of running into it now? They are practically zero. Inflation diluted the density of these monopoles so profoundly that it's likely not a single one exists within our entire observable universe. They are simply so far apart that we will never be able to detect them, effectively solving the problem. The theory of inflation turned out to be incredibly successful, as it not only addressed the three primary challenges of standard cosmology, but also offered a significant and verifiable prediction. The inflationary process could not have been absolutely uniform. According to the principles of quantum mechanics, the inflaton field must have been subject to constant microscopic quantum fluctuations, which are spontaneous and random oscillations in energy. In our everyday world, such fluctuations emerge on minuscule scales and dissipate almost instantly. However, during the inflationary epoch, these tiny ripples were seized by the exponential expansion and stretched to astronomical proportions, becoming permanently etched into the very fabric of space-time. Once inflation concluded, these fluctuations served as the primordial seeds that would guide the formation of the universe's large-scale structure. Regions with a slightly greater energy density acted as gravitational wells, drawing in matter that would eventually coalesce into clusters of galaxies, while areas with a slightly lower density evolved into the vast voids of deep space. The theory of inflation forecasts a very distinct character for these initial fluctuations. They are expected to be almost, but not perfectly, scale invariant, which implies their amplitude should be nearly identical across all scales, with a subtle bias towards larger ones. When instruments aboard satellites, like the Cosmic Background Explorer, or COBE, the Wilkinson Microwave Anisotropy Probe, or WMAP, and particularly the Planck spacecraft, mapped these temperature variations in the cosmic microwave background with unparalleled precision, they discovered the exact pattern the inflationary model had predicted. The spectrum of these fluctuations aligned with theoretical calculations with breathtaking accuracy, marking a resounding triumph. From that point on, inflation transformed from a compelling hypothesis into a fundamental component of the standard cosmological model, which today is often called the lambda cold dark matter or lambda CDM model with inflation. This expanded theory provided an explanation not just for why the universe appears so uniform on a grand scale, but also for why it isn't perfectly so, revealing the origins of galaxies, stars, and ultimately, ourselves. It appeared as though the final answer had been found, and the history of the universe was fully written. We seem to understand its birth, its evolution, and the reasons it is the way we observe it. The monument to the Big Bang was not merely restored, it was augmented with a grand and graceful portico that rendered the entire edifice more coherent and logical. For several decades, the inflationary paradigm reigned over cosmology with seemingly no viable alternatives, and any expressions of doubt were considered fringe. Yet, as is often the case in science, resolving one puzzle can introduce another, far more profound one. Inflation, while mending the fractures in the old foundation, also planted a time bomb beneath the entire structure, a bomb that threatened not just the physics, but the very essence of the scientific method and our position in the cosmos. And that bomb was on the verge of detonation. The theory of inflation was undeniably one of the most pivotal advances in late 20th century cosmology, as it elegantly resolved long-standing problems, delivered successful predictions, and offered a cohesive narrative of the early universe. For a while, a sense of euphoria permeated the scientific community. It felt as though the primary mysteries had been solved, with only minor details left to refine. But as physicists delved deeper into the mathematics and consequences of the inflationary model, the celebratory atmosphere started to dissolve into a growing sense of apprehension. It became clear that inflation, the brilliant savior of standard cosmology, carried with it a set of properties that placed it on extremely unstable ground, where the lines between physics and metaphysics begin to blur. In solving the old conundrums, inflation had opened a true Pandora's box, unleashing concepts that challenge our ability to make scientific predictions at all. The very first issue, which prompted questions from the beginning, concerns the nature of the entity responsible for inflation, the enigmatic inflaton field. What exactly is it? What are its constituents? What are its fundamental properties? To this day, we lack answers to these questions. The inflaton is not any of the known particles within the standard model of particle physics. It is a purely hypothetical entity introduced into the theory out of sheer necessity. We postulate its existence because we require it to account for the observed characteristics of our universe. While this practice is not forbidden in science, for instance, we also posit the existence of dark matter and dark energy to explain observations, the situation with the inflaton is considerably more intricate. The difficulty lies in the fact that to achieve an inflationary period with the precise parameters needed to explain our flat and homogeneous universe, the inflaton field must have very specific, finely tuned characteristics. Its potential energy is required to have a particular, exceptionally flat shape to guarantee a long enough phase of slow rolling, which in turn ensures a sufficiently extended period of inflation. This is what is known as the fine-tuning problem for inflation itself. What this means is that we have merely substituted one fine-tuning issue, the question of why the universe is flat, with an entirely new one, the question of why the inflaton field possesses such a peculiar and specific form. This is analogous to attempting to solve one enigma by inventing an even more profound one. At present, an immense number of distinct inflationary models exist that utilize different kinds of fields, yet not a single one of them arises naturally from any more fundamental theory, like string theory or loop quantum gravity. Inflation continues to be a wonderfully elegant and potent idea, but the physical mechanism behind it remains completely unmoored from established physics. Even so, this is merely the visible tip of a much larger and more troubling iceberg. The true existential crisis for inflationary cosmology is rooted far more deeply in what is known as the problem of eternal inflation. As physicists, notably Andrei Linde and Alexander Vilenkin, delved into the dynamics of the inflaton field, they unearthed a completely unforeseen and counterintuitive reality. It appears that in the majority of plausible models, once inflation begins, it effectively never ceases on a universal scale. So, how can this be? The explanation is found in the very same quantum fluctuations I've previously mentioned. The inflaton field, the engine driving this expansion, is constantly affected by these quantum shifts. In certain regions of space, a random fluctuation can nudge the field back up its energy potential, causing that area to inflate for even longer. Conversely, in other areas, a fluctuation might accelerate the field's slide downhill, bringing inflation to a halt there. Whenever inflation concludes in a specific region, it results in the formation of a bubble, a conventional, hot universe, much like the one you and I inhabit. Within this bubble, the more standard, gradual expansion governed by Hubble's law takes over. Meanwhile, the surrounding space where inflation persists continues to expand exponentially at a vastly greater rate. This dynamic establishes a scenario where the inflating regions consistently outgrow the volume of the regions where inflation has ceased. Consequently, on a global scale, the inflating spacetime will perpetually spawn new universe bubbles, each of which could possess its own distinct set of properties. This process is endless, suggesting our universe is merely one of an infinite number of such bubbles adrift in an eternally expanding, boiling ocean of inflating space. From this mechanism, the concept of the multiverse emerges, almost as an unavoidable consequence. While this vision is at first thrilling in its grandeur, it poses a profound challenge to the scientific method, a dilemma known as the measure problem. If an infinite number of bubble universes exist, then within this boundless collection, any outcome not prohibited by the laws of physics is possible. Some universes might have different physical constants, where stars could never form, while others might be nearly identical to ours, and still others could host utterly alien scenarios. This raises the central question: how can we formulate scientific predictions in such a reality? For instance, inflation theory suggests our universe should be flat, yet if the multiverse generates an infinite number of both flat and severely curved universes, our observation of a flat one is no longer a solid prediction. It becomes a matter of chance, a consequence of our particular bubble having the right conditions. Any feature of our world can then be explained away by the anthropic principle, the idea that if things were different, we simply wouldn't be here to observe them. The issue is that a theory capable of explaining everything ultimately explains nothing. The philosopher Karl Popper taught us that a scientific theory must be falsifiable, meaning it must make specific, risky predictions that can be experimentally verified. If an experiment contradicts a prediction, the theory is disproven. But how can you falsify eternal inflation? If we were to measure a property of our universe that clashes with a favored inflationary model, its supporters could simply claim that we occupy a rare atypical bubble in the multiverse. This response renders the core theory itself immune to refutation, and many critics argue this places it outside the realm of traditional science. Paul Steinhardt, one of inflation's original architects, has become its most ardent critic for precisely this reason. He contends that instead of solving the fine-tuning problem, Inflation compounds it by generating an infinite spectrum of results without offering any method to calculate the probability of our universe emerging. This effectively neuters the predictive capacity of cosmology. Furthermore, the problem of the singularity remains unresolved. Remember, inflation serves as a prelude to the Big Bang, explaining the conditions that precipitated it, but it offers no insight into what preceded inflation itself. In 2003, a theorem proven by Arvind Borde, Alan Guth, and Alexander Vilenkin established that any spacetime which is, on average, expanding cannot be eternal into the past. It must have a beginning. This implies that even an eternally inflating multiverse had to originate from something, bringing us right back to the initial singularity, a state of infinite density and temperature, where our known laws of physics collapse. Inflation managed to push this fundamental puzzle back one step, but it did not eliminate it, leaving the ultimate origin of our cosmic history as its greatest mystery. So where does this leave us? Inflation stands as a brilliant and transformative concept that elegantly accounts for the homogeneity, flatness, and structure of our universe. However, this explanation comes at an incredibly steep price. We are asked to accept a hypothetical, unobserved field with finely tuned properties, leading us to the nearly inescapable conclusion of an infinite multiverse that undermines the very predictive power of science, all while leaving us confronting the enigma of an absolute beginning. This profound conceptual discomfort has prompted many physicists, including some of inflation's founders, to question if there is another way. They wonder if a more elegant, more economical explanation exists, one that doesn't rely on such radical and potentially untestable assumptions. In their search, they have revisited an idea as old as time, long dismissed by modern physics as heresy: the notion that the universe may not have had a beginning at all. Before we get into the intricate specifics of contemporary cyclic theories, I want you to join me in taking a brief step back. Let's move beyond the equations and observational data for a moment to consider the very notion of time and creation from the perspective of human intellectual history. The concept of the universe that we now take for granted, a linear timeline with a singular origin in the Big Bang that progresses towards some future, is, in fact, a fairly recent development. For thousands of years, an entirely different and far more cyclical worldview was the dominant perspective. I invite you to travel with me in your mind to ancient India, long before the eras of Hubble and Einstein. Within Hindu cosmology, as detailed in scriptures like the Puranas, time is not perceived as a straight line, but as an unending succession of cycles known as kalpas. Each kalpa represents a single day for Brahma, the universe's creator, and spans 4.32 billion years, a duration that remarkably mirrors the modern estimate for the age of our Earth. At the start of every kalpa, Brahma awakens and brings the world into existence, which then proceeds through various epochs or yugas, declining from a golden age into a dark one. At the kalpa's conclusion, Brahma's night, equal in length to his day, commences, and the world is destroyed and dissolves into primordial chaos, only to be reborn when Brahma awakens once more. This principle of eternal recreation was not confined to India, as we can find similar ideas reflected in numerous other cultures. The ancient Egyptians observed cycles in the annual flooding of the Nile, and in the cosmic journey of the sun god Ra, who, metaphorically, died each night in the underworld only to be reborn at dawn. Similarly, the ancient Greek, Stoic philosophers, including Zeno and Chrysippus, conceived of ekpyrosis, the belief that the universe is periodically obliterated in a massive cosmic fire before being perfectly recreated down to the last detail, an endless repetition they termed the Great Year. You can even see this in the traditions of Native American peoples like the Aztecs and the Maya, who spoke of successive worlds, or suns, that were cyclically created and then destroyed by their deities. Why was this concept so pervasive across the ancient world? The most likely reason is that it was a direct reflection of the environment our ancestors witnessed around them. Nature is filled with cycles. Day follows night, seasons change from winter to summer, and the moon transitions through its phases. Life itself is a cycle of birth, death, and the generation of new life, making it a natural and intuitive leap to assume that the entire cosmos operated on the same eternal rhythm. This cyclical perspective on the universe offered a profound sense of stability and order in what could often feel like a chaotic and unpredictable existence, suggesting that nothing ever truly perishes for good. So, what led to the emergence of our current linear understanding of time? The majority of intellectual historians point to the rise and influence of the Judeo-Christian and Islamic faiths. In these Abrahamic traditions, history is framed with a distinct beginning, a singular act of divine creation out of nothing, a pivotal central event, and a clear trajectory toward a final endpoint, such as the Last Judgment. In this view, history is not a repeating circle, but a straight arrow shot by a creator toward a predetermined target. This linear model of time became deeply embedded in Western culture, providing the intellectual groundwork not just for theology, but also for the philosophy of history, the concept of progress, and eventually, the scientific worldview that took shape during the Enlightenment. When cosmology matured into a rigorous scientific discipline in the 20th century, it naturally inherited this linear paradigm. The Big Bang Theory, positing a unique moment of creation roughly 13.8 billion years ago, aligned seamlessly with this established cultural framework, effectively becoming a scientific parallel to the story of Genesis. This isn't to say the scientists themselves were religious, but rather that the fundamental structure of their thinking and their intuition about time had been molded by centuries of the linear model's dominance. This cultural inheritance helps explain why the first scientific proposals to reconsider a cyclical universe were met with such staunch opposition. The notion that the Big Bang might not have been the absolute origin of everything, but simply one event in an infinite series, struck many as counterintuitive and almost heretical to the prevailing scientific dogma. Why have I taken you on this tour through the history of ideas? It's because doing so helps you grasp two critical points. First, it demonstrates that the idea of a cyclical universe isn't some strange, fringe concept dreamed up by a few modern physicists. It is a fundamental archetype within human consciousness, an ancient intuition about reality's true nature. When contemporary science explores cyclic models, it may be giving rigorous mathematical form to what mystics and philosophers have been discussing for millennia. Second, and perhaps more importantly, this historical context frees us from the constraints of our own intellectual habits. It serves as a powerful reminder that our current standard model of cosmology is not the only conceivable way to understand the universe. By becoming so accustomed to the idea of the Big Bang as the ultimate beginning, we run the risk of intellectual dogmatism. Acknowledging that other, equally ancient and profound cosmological stories exist helps to keep our thinking flexible and open to new possibilities. This perspective allows you to view modern cyclical theories not as peculiar outliers, but as serious contenders in cosmology. supported by both stringent physics and a profound philosophical and cultural legacy. With that foundation, we can now turn our attention back to the physics. You will learn how scientists in the mid-20th century made their first attempt at creating a mathematically sound model of a cyclical universe, and discover why that initial effort was doomed to fail against one of nature's most unyielding principles. This failure was so profound that it effectively erased the concept of cosmic cycles from serious scientific discussion for over a decade. However, it was precisely by dissecting the reasons for this setback that contemporary physicists eventually discovered a path forward. The concept of eternal return, with its deep roots in philosophy, was bound to capture the imagination of physicists once they grasped the dynamic character of the cosmos in the 20th century. Following the work of Friedman, Lemaitre, and Hubble, which solidified the model of an expanding cosmos, a logical question emerged. What comes next? If the universe is continually expanding, is it possible that gravity, with its relentless pull, could ultimately halt this expansion and draw everything back together? The idea presented a beautifully elegant symmetry. The universe would be born from an incandescent singularity, grow to its maximum extent, and then collapse back into another fiery point, a big crunch. Following this collapse, a new rebound would trigger another Big Bang, restarting the entire cycle. This compelling narrative came to be known as the oscillating universe, and one of its earliest and most insightful investigators was the American theoretical physicist Richard Tolman. During the 1930s, Tolman began to formulate mathematical models of such an endlessly pulsating universe, operating within the framework of Einstein's general theory of relativity. But Tolman wasn't merely a mathematician. He was a pioneering figure in statistical mechanics and thermodynamics. He knew with certainty that any cosmological model had to conform not just to the laws of gravity, but also to the core principles of thermodynamics. And it was here that he faced a severe disappointment. The primary, and at that time seemingly final, barrier to an eternal cycle was one of nature's most fundamental and unforgiving laws, the second law of thermodynamics. What exactly does this law declare? In its most basic formulation, it states that within any isolated system, the total entropy will never decline. It can only remain constant or rise over time. But what exactly is entropy? Entropy is among the most intricate yet most vital concepts in all of physics. While it's frequently described as a measure of a system's disorder or chaos, that definition isn't quite precise. A more accurate explanation is that entropy quantifies the number of different microscopic arrangements that can produce a system's observed macroscopic state. Let's explore this with a straightforward illustration. Picture a box with a divider down the middle, where gas molecules occupy the left side, while the right side is a vacuum. This configuration represents a state of low entropy. The reason is its high degree of order. All molecules are confined to one area, and there are comparatively few ways to arrange them to achieve this. Now, if you remove that divider, the gas molecules will spread out chaotically, rapidly occupying the entire container. The system transitions into a state of high entropy, a disordered condition reflecting the unimaginably vast number of ways the molecules can be positioned to be evenly distributed throughout the box. The system naturally evolves from a less probable, ordered arrangement to a more probable, chaotic one. Crucially, you will never witness all those gas molecules, without any external force, spontaneously reassemble themselves in the left half. This process is irreversible, setting the arrow of time as defined by increasing entropy on a one-way flight. Let's look at another example. If you place a drop of black ink into a glass of water, you begin with a highly ordered state, where the water and ink are separate. Very quickly, however, diffusion will cause the ink to blend uniformly, transforming the clear water into a gray fluid. The system's entropy has increased, and regardless of how long you observe it, you will never see that gray mixture spontaneously separate back into a concentrated black droplet. Likewise, a shattered egg will never put itself back together, and heat will always flow from a hotter object to a colder one, never in reverse. All of these everyday phenomena you see are expressions of the second law of thermodynamics. It is this law that establishes the direction of time, creating a clear distinction between the past and the future. Richard Tolman understood that this principle must be applied to the universe as a whole. He reasoned that within each cycle of expansion and contraction, irreversible processes that generate entropy had to be occurring. The most significant of these processes is the formation of stars. Stars, such as our own Sun, take highly ordered matter like hydrogen and helium and, through thermonuclear fusion, transform it into more chaotic forms of radiation, namely the light and heat that disperse across the cosmos. Every single photon released by a star carries with it a small amount of entropy, and this process is completely irreversible. The light that has journeyed from a star will never reconverge to recreate the hydrogen from which it came. Tolman performed meticulous calculations that led him to a discouraging conclusion. If the universe does oscillate, then each cycle must inevitably generate new radiation and other forms of entropy, including things like black holes and neutrinos. As the universe begins to contract, this accumulated entropy does not vanish. Instead, it is compressed along with all the matter, which makes the point of the Big Crunch even hotter and more chaotic than the point of the Big Bang that preceded it. Consequently, every subsequent bounce would be initiated with a greater amount of energy and entropy. This implied that the maximum size the universe reached in each new cycle would be larger than in the one before it. Furthermore, the duration of each successive cycle would also be longer, shattering the elegant symmetry of a perfectly repeating, eternal cosmos. This realization completely dismantled the elegant notion of a cosmos repeating itself forever. The cosmic cycles were not uniform, but were instead growing progressively larger and more extended over time. You can visualize it less like an ideal pendulum in perpetual motion and more like a spring that stretches further and weakens with each successive oscillation. If you were to trace this model back into the past, the cycles would inevitably become shorter and more compact, leading you to a first, smallest cycle, and thus back to a definitive origin. Conversely, looking toward the future reveals that after a finite number of bounces, the expansion would become so immense that gravity would lose its grip, sending the universe into an endless expansion that culminates in heat death, a state of ultimate entropy where nothing can happen. The issue of a singularity and a cosmic beginning refused to go away, making the idea of an eternal cycle fundamentally unworkable. Compounding this was a distinct problem rooted in relativity concerning the bounce itself. General relativity predicts that as matter collapses gravitationally, there is nothing to prevent it from crushing down into a singularity, a point where density and the curvature of space-time become infinite, and all known physical laws break down. There was simply no known mechanism that could compel a collapsing universe to rebound and start expanding again. The standard theory pointed not to a bounce, but to a final, irreversible collapse, marking the end of space and time. To make the model work, one had to introduce some form of new, exotic physics, an undiscovered repulsive force that would only activate at unimaginably high densities. In the 1930s, however, no grounds for such a hypothesis existed. These two critical flaws, the relentless growth of entropy and the unavoidable singularity during contraction, delivered a fatal blow to the early cyclical models. The work done by Tolman was so thorough and persuasive that for nearly 50 years the concept of an oscillating universe was dismissed as a beautiful but ultimately flawed idea, a topic that was effectively closed. As a result, cosmologists directed their energies toward refining a model with a single Big Bang, which at least sidestepped these glaring thermodynamic inconsistencies. The discovery of the cosmic microwave background radiation in 1965, while a major victory for the Big Bang model, was also interpreted as another argument against cyclical cosmology. The immense quantity of photons in this relic radiation acts as a massive reservoir of entropy. With each new cycle, additional photons generated by stars would add to this reservoir, causing the radiation density to climb relentlessly from one cycle to the next. This would only intensify the problem that Tolman had originally outlined. So, by the end of the 20th century, anyone wishing to resurrect the cyclical model had to answer two essential questions. First, how could the second law of thermodynamics be circumvented? A mechanism was needed to either reset or dilute the entropy from the previous cycle, allowing the next one to begin in an identical low-entropy state. Second, how could the singularity problem be resolved? A solution required either preventing the Big Crunch entirely or discovering new physics that could transform the end-of-time singularity into a gateway to a new beginning. For decades, these challenges appeared utterly insurmountable. But at the dawn of the 21st century, theoretical physics underwent two major revolutions that changed everything. The first was the rise of string theory and its extension M-theory, which proposed the existence of extraspatial dimensions. The second revolution was a rapidly advancing comprehension of dark energy, the enigmatic force driving the accelerated expansion of our universe. It was the fusion of these new concepts that gave rise to the first modern cyclical models. They offered a completely fresh approach to overcoming the old, seemingly permanent barriers, suggesting the Big Bang might not have been a collapse at all, but an event on a far more magnificent scale. At the turn of the millennium, cosmology was in a peculiar position. On one hand, the inflationary Big Bang model appeared to be on the verge of total triumph, with observations of the cosmic microwave background offering brilliant confirmation of its predictions. On the other hand, the conceptual issues we've discussed, such as eternal inflation, the multiverse, and the singularity, were stirring a growing sense of unease among many theorists. It felt as if science had hit a wall, where further progress demanded a leap into almost metaphysical territory. This climate of intellectual tension set the stage for the first rigorously mathematical alternative to inflation in decades. Ironically, one of its principal architects was Paul Steinhardt from Princeton University, a physicist who had himself helped construct the theory of inflation. Working alongside his colleague Neil Turok and with Justin Khoury and Bert Overoot, Steinhardt crafted a cosmological model so profoundly different from its predecessors that it demanded a new vocabulary and fresh imagery. They named it the ekpyrotic model, taking inspiration from the ancient Stoic term ekpyrosis, which means conflagration or a world-consuming fire. This was no mere adjustment of existing ideas. It was constructed upon an entirely new foundation drawn from the most advanced and abstract realm of theoretical physics, M-theory. So, what is M-theory? It is, in essence, an effort to weave together the 5 distinct versions of string theory and supergravity into a single, unified theory of everything. A central concept of both string theory and M-theory is the proposition that our universe may possess more dimensions than the 3 of space and 1 of time that we directly experience. According to this theory, the extra dimensions are either coiled into tiny bundles beyond our ability to observe, or our 3-dimensional reality is essentially a surface, a membrane, drifting within a higher dimensional space. It is this latter concept that Steinhardt and Turok used as the cornerstone of their cosmology. They proposed that everything we can see, every galaxy, star, and planet, including you and me, resides on an enormous three-dimensional membrane, which they shortened to brain. Our brain, however, is not solitary. It floats within a space that has a fourth spatial dimension, which theorists have dubbed the bulk. Parallel to our own brain, and separated by a microscopic distance within this bulk, there is another, identical three-dimensional brain. While this parallel reality might contain its own world and matter, we can never see or touch it, as the fundamental forces of the standard model, such as electromagnetism and nuclear forces, are permanently confined to our own brain. The only force theorized to move freely between these brains through the bulk is gravity. Within this framework, the entire history of the universe unfolds in a completely different way. The Big Bang, which you likely think of as the absolute beginning of everything, is re-envisioned in the ekpyrotic model not as the origin of time and space, but as the outcome of a recurring and cataclysmic event, the collision between our brain and its parallel neighbor. To help you picture this, the cycle starts with two parallel brains that are nearly empty, incredibly cold, and almost perfectly still, separated by a tiny gap in that extra dimension. A faint attractive force exists between them, much like the one attributed to dark energy, which begins to draw them together with extreme slowness over an unimaginably vast period lasting trillions upon trillions of years. During this profoundly long era of convergence, almost nothing happens on the brains as they continue to cool, expand, and become ever smoother and more vacant. As they draw nearer, the attractive force between them intensifies, causing their approach to accelerate until they finally collide. This impact happens not at a single location, but almost instantaneously across their entire infinite surfaces, releasing the kinetic energy of their movement as an immense blast of heat and radiation, forming the very same hot, dense fireball of particles we associate with the Big Bang. For any observer living on one of these brains, this collision would look exactly like the genesis of a hot, rapidly expanding universe. Following the impact, the brains do not annihilate each other. Instead, depending on the version of the model, they might pass right through one another or rebound and begin moving apart once again. The immense energy from this event fuels the expansion of each brain's fabric, launching the phase of cosmic expansion that we find ourselves in today, where the universe cools and allows for the formation of galaxies, stars, and life. This expansion, propelled by a force resembling dark energy, persists for trillions of years, causing the universe to grow progressively colder and more desolate. As stars burn out and black holes evaporate, the density of all matter and radiation plummets to nearly zero, returning the universe to an empty, cold, and smooth state. At this stage, the cycle completes its loop, as the attractive force between the brains reasserts its dominance, halting their separation and beginning the slow journey back toward each other for the next cosmic collision. This model completely reframes our conception of a beginning, transforming the Big Bang from an absolute starting point into a transitional phase, a bridge between one cosmic cycle or eon and the next. In this view, time itself was not created in the Big Bang, but has existed eternally. Our universe is like a phoenix, reborn not from its own ashes, but from the powerful impact with its unseen, mirrored twin. To make this concept even more accessible, I can offer you a simple analogy. Imagine two parallel rubber sheets, representing our brains, stretched taut. They start out still, and then we slowly bring them together. The moment they make contact, you hear a loud clap. That is our Big Bang. This impact generates a wave that travels through the sheets, making them vibrate and expand, which symbolizes the expansion of our universe. Eventually, these vibrations die down, and the sheets become calm and flat once more, poised for a new convergence. So what elevates this seemingly fantastical story into the realm of a scientific theory? It's not merely that it provides a new creation narrative, but that it also resolves the very same problems that the theory of inflation was conceived to fix. And according to its creators, it does so in a more natural way. For instance, it addresses the horizon problem, which asks why the universe appears so uniform in every direction. The inflationary model explains this uniformity by proposing the super-rapid expansion of a minuscule, homogeneous region. The ekpyrotic model, however, presents a completely different explanation. It argues that the universe's homogeneity is the natural result of the incredibly long, trillion-year phase of slow contraction as the branes approached one another. Over this immense timescale, any irregularities would have had more than enough time to smooth out, ensuring the branes were already perfectly uniform by the time they collided. The flatness problem finds a similarly elegant solution in this model. Throughout the long epoch leading up to the collision, the dark energy driving the brane's expansion naturally causes them to become increasingly flat. While inflation theory posits that this flattening happened in a tiny fraction of a second, the ekpyrotic model suggests the same outcome was achieved far more gradually over trillions of years. Consequently, by the time of the collision, the branes would already be almost perfectly flat, just as we observe our universe to be. Therefore, our universe's flatness isn't the product of precise fine-tuning or some incredibly rapid event, but rather the natural outcome of a tremendously long evolutionary process. So, what about the primordial fluctuations that seeded the galaxies? Inflation accounts for these as quantum fluctuations within the inflaton field, whereas the ekpyrotic model provides its own distinct mechanism. In the ekpyrotic view, the branes are not perfectly smooth during their slow convergence. They possess their own quantum fluctuations, which you can imagine as a sort of microscopic ripple. Because of these ripples, different areas of the branes don't collide at the exact same instant, but with tiny variations in timing. The collision happens a fraction of a moment sooner where a trough on one brane encounters a crest on the other, making that spot slightly hotter. Conversely, where two troughs meet, the collision is slightly delayed, resulting in a lower temperature. This microscopic difference in the timing of the collision is what generates the precise temperature fluctuations we observe in the cosmic microwave background, which ultimately act as the nucleation points for galaxy formation. Calculations revealed that the spectrum of fluctuations predicted by the ekpyrotic model is virtually identical to inflation's predictions, meaning both theories align with observational data. A new theory had thus emerged, capable of everything inflation could do, explaining the universe's flatness, homogeneity, and structure, but without inflation's most unsettling implications. The ekpyrotic model has no need for eternal inflation, and consequently, no multiverse. It proposes just a single universe, or more accurately, a pair of brane universes, that perpetually engages in an endless sequence of cycles. This framework also offers a potential way around the initial singularity problem, since the collision takes place at a finite temperature and density, allowing it to be described by known physics without any need for infinities. Of course, this model introduces its own set of complexities. Its foundation rests on the existence of extra dimensions and branes, which are hypothetical elements of M-theory that currently lack any experimental validation. The mechanics of the collision and the subsequent bounce also need much more detailed development. Despite these challenges, its appearance in the early 2000s was a genuine breakthrough, as it proved that inflation was not the only conceivable answer. This new perspective brought the concept of cosmic cycles back from the fringes of philosophy into the core of theoretical physics. It presented cosmologists with an exciting new dilemma. How do you choose between these two starkly different yet equally plausible accounts of our universe's earliest moments? As is always the case in science, the resolution must be found in observation. The debut of the ekpyrotic, or its later iteration, the Cyclic model by Steinhardt and Turok, was like a gust of fresh air in the somewhat stagnant field of cosmology. It provided more than just an alternative. It offered a completely different philosophy for addressing fundamental cosmic puzzles. If you think of inflation as a swift surgical procedure that corrects the universe's defects in a split second, then the Cyclic model is more akin to a long-term meditative therapy, which patiently and naturally brings the cosmos into its ideal state over trillions of years. Let's now explore, methodically and in detail, how this new paradigm confronts not only the familiar problems of the horizon and flat geometry, but also the seemingly insurmountable barrier of entropy, which caused all previous cyclic theories to fail. We will start with the bedrock issue, resolving the fine-tuning of initial conditions. As you'll recall, the standard Big Bang model, without inflation, demanded that the universe begin with unimaginably precise parameters, being almost perfectly flat and homogeneous from the start. Inflation addressed this by suggesting the universe could have been born chaotic and curved, only to be rapidly purified and flattened by an explosive expansion. The Cyclic model presents a third way. It proposes that we don't need to be concerned with the initial conditions at the moment of the Big Bang, that is, at the collision of the brains. The reason is that these conditions are not truly initial at all. Instead, they are entirely shaped by the events of the preceding cycle, which unfolded over trillions of years before the collision ever took place. Dark energy assumes a pivotal role in this entire process. Back in the 1990s, astronomers made the startling discovery that our universe isn't just expanding, but that its expansion is accelerating. The agent responsible for this acceleration is a mysterious substance with negative pressure that permeates all of space, which we call dark energy. In the Cyclic model from Steinhardt and Turok, dark energy is not merely a strange feature of our current epoch. It is the primary engine that propels the entire cosmic cycle. Let's visualize our brain universe just after another collision has occurred. It is incredibly hot and dense, and it starts to expand. Over the first few billion years, matter and radiation are the dominant forces, and their gravitational pull works to slow this expansion down. It is during this phase that galaxies, stars, and planets take shape. But as space continues to expand, the density of matter and radiation drops, until eventually the density of dark energy, which is believed to remain constant, becomes the dominant component. From that point forward, the universe enters a phase of accelerated expansion that will persist for trillions of years. It is precisely this prolonged period of accelerated expansion that functions as the great purifier of the cosmos. So what does it actually accomplish? First, it resolves the problem of flat geometry. This accelerated expansion acts very much like inflation, only at a far more leisurely pace, stretching space and effectively ironing out any residual curvature. By the conclusion of this phase, our brain universe becomes almost perfectly flat, irrespective of its initial state. Second, this process solves the problem of homogeneity. The relentless expansion pushes all existing structures, such as galaxies and clusters, so far from one another that they cease to be in contact. The universe grows incredibly uniform and empty as a result. Any temperature variations that might have survived from the previous cycle are smoothed out to the point of being negligible. Consequently, by the time the brains finally halt their expansion and start moving toward each other again, they have already been made perfectly ready for the next cycle. The necessary starting conditions for the subsequent cosmic collision are a universe that is flat, cold, empty, and uniform. The cyclic model sidesteps any need to speculate about the universe's state at the dawn of time, because, in this view, it has no beginning. Instead, the state preceding each Big Bang is the direct and unavoidable outcome of physical processes from the previous eon, creating a powerful and efficient framework that honors the principle of cosmological naturalism, the idea that the universe, on its own, must produce the properties we observe, without any fine-tuning or exotic initial conditions. Now we must turn to the most challenging issue, the problem of entropy, which proved fatal for Richard Tolman's earlier models. How does this modern cyclic model manage to circumvent the second law of thermodynamics? With every cycle, stars are born and radiate photons, while black holes, objects of immense entropy, come into being. You have to wonder where all this accumulated disorder goes, as it seems the next cycle should logically start with far more entropy than the last. The cyclic model provides an answer in two stages, with the first and most critical part once again involving the phase of accelerated expansion. As the universe expands, its volume increases exponentially, causing the entropy density, the quantity of entropy within any given volume, to plummet to nearly zero. Picture having a glass of murky water where ink has thoroughly mixed with the liquid, representing a high entropy state. If you were to pour that glass into the Pacific Ocean, the total amount of ink has technically increased, but its density becomes so minuscule that the ocean's water appears just as clear as before. In much the same way, cosmic expansion dilutes the entropy generated in one cycle across an unimaginably vast expanse of space, ensuring that by the time the contraction phase begins, the entropy density from matter and radiation is negligible. But this raises a new question about black holes, which are the undisputed champions of entropy. The Bekenstein-Hawking formula tells us a black hole's entropy is proportional to its event horizon's area, and a single supermassive black hole can harbor more entropy than all the cosmic microwave background radiation in the entire observable universe. Since black holes are compact objects, expansion does not solve this particular problem. The model's solution to this puzzle is remarkably elegant. Throughout the phase of accelerated expansion, as galaxies drift ever farther apart, black holes become increasingly isolated, eventually consuming all nearby matter. Critically, during this era, they start to dominate the universe's gravitational field. Calculations reveal a fascinating outcome. It is these black holes, not conventional matter or radiation, that produce the quantum fluctuations, destined to become the seeds for new galaxies in the next cosmic cycle. In this way, the black holes from a previous eon don't just vanish, they actually imprint the blueprint for future structures onto the next universe. Regarding the entropy itself, the pivotal insight is that in this model, our universe never collapses into an infinitesimal point. The contraction only occurs in the additional fourth dimension, the space between branes, while our familiar three-dimensional universe continues to expand. This prevents black holes from ever merging into a single, colossal singularity. Instead, they persist, potentially evaporating over vast timescales via Hawking radiation, which means the bulk of their entropy remains safely confined within their event horizons, never compromising the smoothness and uniformity of the new cycle. To summarize, the Steinhart-Turok cyclic model puts forward a grand reset mechanism that unfolds over trillions of years. Dark energy-driven accelerated expansion accomplishes three objectives simultaneously. It flattens space-time, it smooths out inhomogeneities, and it dilutes the entropy of matter and radiation to almost nothing. Meanwhile, the colossal entropy of black holes is either kept isolated or its fluctuations are repurposed to generate structure in the following cycle. This offers a beautifully self-contained picture that doesn't rely on a hypothetical inflaton field or a metaphysical multiverse, using only the ingredients we know to exist: gravity, dark energy, and the extra dimensions suggested by string theory, to replace a singular beginning with an eternal, self-renewing process. Yet, as brilliant as this model is, it wasn't the sole attempt to bridge the gap of eternity. Around the same time, another great thinker of the 20th century approached the issue from a completely different perspective, proposing a cosmic cycle that was even more radical. While the Steinhardt-Turok model emerged from the landscape of string theory, the idea we are about to explore was born from one man's deep contemplation of time, entropy, and space-time geometry. That man is Sir Roger Penrose, the renowned British mathematician and physicist, a collaborator of Stephen Hawking, and a Nobel laureate for his work on black holes. His theory, known as conformal cyclic cosmology, or CCC for short, presents a vision of eternity that feels less physical and more platonically geometric. Penrose does away with branes and extra dimensions entirely. Instead, he devises a method to seamlessly join the end of one universe to the beginning of the next, using nothing more than elegant mathematical symmetry. To grasp Penrose's concept, you must join me on a conceptual journey to the universe's very distant future, far beyond the trillions of years we've been discussing. To understand the ultimate fate of the universe, you and I must project our thoughts forward by googles of years, that is, 10 to the 100th power, and even beyond. If the cosmos continues its dark energy-driven expansion indefinitely, modern physics offers a rather grim forecast. In just a few trillion years, the last stars, which are the red dwarfs, will finally exhaust their fuel. At that point, galaxies will transform into desolate graveyards populated by black holes, neutron stars, and frigid white dwarfs. Over even more immense stretches of time, gravitational forces will slowly dismantle these stellar remnants. The galaxies themselves will dissolve as their contents are flung into the ever-expanding void to drift in isolation. Even planetary bodies will be violently stripped from their orbits, leaving them to wander alone. The subsequent phase involves the disintegration of matter itself, as many grand unified theories propose that protons are not fundamentally stable. On a timescale of roughly 10 to the 32nd power years, they are expected to decay into lighter particles like positrons and photons. This process implies that, given enough time, all baryonic matter, the very substance that constitutes you and me, will eventually vanish, converting entirely into radiation. The only things left will be black holes and an incredibly thin dispersion of photons, neutrinos, and other particles with little to no mass. However, as Stephen Hawking demonstrated, black holes are not immortal. Quantum phenomena at the event horizon cause them to gradually evaporate by emitting particles, a process we call Hawking radiation. For the colossal black holes that reside at the centers of galaxies, this evaporation is extraordinarily slow, taking approximately 10 to the 1 power 100th power years to complete. Yet, on an eternal timeline, even this immense duration is finite. This brings us to the final portrait of the far distant future, where all black holes have evaporated and all matter has decayed. The universe will become an almost perfect vacuum, containing only a vanishingly sparse, near absolute zero background of photons and possibly gravitons, representing a state of maximum entropy often called the heat death of the universe. This appears to be the definitive conclusion, an irreversible endpoint. But it is precisely here that Roger Penrose introduces his brilliant and deeply counterintuitive concept. He poses a disarmingly simple question about this future cosmos, which is composed almost entirely of massless particles moving at the speed of light. In such a universe, devoid of any material objects to function as measuring rods or timepieces, do the very ideas of size and time lose their meaning? A photon, for instance, does not perceive the flow of time. From its perspective, the start and end of its cosmic journey happen at the same instant, regardless of the billions of years that pass for us. A universe populated exclusively by photons would have no internal clock, no temporal standard. By the same token, a cosmos without massive particles lacks any inherent ruler or sense of scale, since there are no atoms of fixed size or planets to establish a frame of reference for distance. In such a reality, concepts like large and small, or long and short, forfeit their physical significance. The only thing that persists is the causal structure, the network of which events could potentially cause which other events. And Penrose posits that this structure is perfectly described by conformal geometry. He then argues that this same principle applies to the Big Bang. In the universe's earliest moments, it was so intensely hot that the energy of particles vastly exceeded their rest masses, causing electrons, protons, and others to behave as if they were massless. Consequently, Penrose asserts that the physics of the nascent universe must also have been conformally invariant. This is where the mathematical elegance of his theory comes into play. We are presented with two distinct states: the infinitely remote future of one cosmic cycle, or eon, and the Big Bang that marks the dawn of the next. Because both of these states are governed by the same scale-independent conformal physics, Penrose shows that a mathematical procedure known as a conformal transformation can be applied. This operation compresses the infinite future of the first eon into a finite boundary, and simultaneously stretches the initial singularity of the second one, allowing these two boundaries to be smoothly joined together. The infinitely distant future of our eon thus becomes the zero point, the Big Bang, for an observer in the succeeding one. This framework resolves the problem of the initial singularity in a manner entirely different from something like the brain model. Instead of avoiding the singularity, it is recontextualized not as a point where physics fails, but as a natural consequence of our conformal rescaling. For any hypothetical observer capable of crossing this boundary, the transition would be perfectly seamless. But this raises a critical question about the second law of thermodynamics and entropy. The distant future is a condition of maximum disorder, heat death, whereas the Big Bang is characterized by an incredibly high degree of order, or low entropy. How can a state of chaos be equivalent to a state of order? This is arguably the most refined and compelling aspect of Penrose's theory. He contends that our understanding of entropy is flawed in a cosmological setting, where we typically link it to the disorderly distribution of matter and radiation. Penrose proposes that the primary contributor to cosmic entropy is not matter, but the gravitational field itself. In the primordial universe, the gravitational field was extraordinarily uniform and smooth, representing a state of very low gravitational entropy. As the universe evolves, gravity causes matter to clump together, forming stars, galaxies, and eventually black holes. And this very process of clumping signifies the growth of gravitational entropy. Black holes, as we now understand, are entities that possess the highest possible entropy for their size. So what exactly happens at the conclusion of an eon? While the material entropy associated with radiation and particles reaches its maximum, Penrose argues that the gravitational entropy is effectively purged from the universe. This is because it has become entirely concentrated within black holes. As these black holes slowly evaporate over countless eons, they take that concentrated gravitational entropy with them, paving the way for a new, low-entropy beginning. Through the process of Hawking evaporation, black holes ultimately cease to exist, taking their colossal entropy with them. Consequently, as an eon draws to its absolute close, the universe reverts to a condition of exceptionally low gravitational entropy, once again becoming smooth and uniform, much like it was at its inception. This observation allows Penrose to draw a conclusion that seems paradoxical at first. The Big Bang represented a low-entropy state not due to its small size and high temperature, but because its gravitational field was extraordinarily uniform. The distant future, despite being a state of maximum material entropy, also becomes a state of low gravitational entropy once the black holes are gone, which is precisely what permits the identification of their conformal geometries. The low entropy at the beginning of our universe is, in effect, the forgotten information from the high entropy conclusion of the preceding eon. In this model, known as conformal cyclic cosmology, you don't find any bounces or cosmic collisions. Instead, there is just a seamless, unending succession of eons. Each of these eons is born from a Big Bang that serves as the conformal continuation of the far future of the one before it, and each culminates in a heat death that, in turn, sparks the Big Bang for the next. It's an everlasting cycle of cosmic renewal, powered by two essential processes: the expansion of gravitational entropy that builds structures and black holes, and the subsequent resetting of that entropy via Hawking evaporation.
This presents an incredibly ambitious and all-encompassing vision that seeks to weave together thermodynamics, general relativity, and quantum mechanics. However, just like any theory in science, it holds no value without predictions that can be tested. And the predictions that Penrose puts forward are arguably the most remarkable of all. What truly separates a physical theory from philosophy, or mere mathematical exercises, is its capacity to produce distinct, verifiable predictions. A theory can be astonishingly beautiful and elegant, but it risks being nothing more than an intellectual curiosity if it offers no means of experimental validation. It is precisely on this point, the question of experimental proof, that the paths of inflation and cyclic models diverge dramatically, presenting us with entirely different research avenues for the future. First, let's explore what aspects of the Steinhardt-Turok cyclic model we can actually test. Its primary and most definite prediction revolves around gravitational waves. These waves are disturbances in the very structure of space-time, which were first predicted by Einstein and directly observed for the first time in 2015 at the Laser Interferometer Gravitational Wave Observatory, or LIGO. Cosmological models suggest that primordial gravitational waves should have been created in the infant universe and continue to traverse space to this day. On this topic, inflation and the cyclic model offer completely different forecasts. Inflation, as a process driven by quantum fluctuations at incredibly high energies, predicts the creation of a background of gravitational waves across a vast spectrum of wavelengths, including extremely long ones that are comparable to the scale of the observable universe. These long waves are expected to have left a unique signature on the polarization of the cosmic microwave background, a pattern known as B-modes. The search for these B-modes has become a sort of holy grail for contemporary cosmological experiments, as their discovery would provide nearly undeniable proof in favor of inflation. So, what does the cyclic brane collision model anticipate? Since the collision it proposes happens at energies far lower than those of inflation, it predicts a primordial gravitational wave background that is many orders of magnitude weaker. This background would be so faint that detecting it through the B-mode polarization of the cosmic microwave background would be practically impossible.
This gives us a clear-cut standard for deciding between the two models. If future, more sensitive experiments, like the Lightbird satellite or the next generation of ground-based observatories, do detect primordial B modes, it will deal a severe blow to the cyclic model and represent a major victory for inflation. Conversely, if no B modes are detected despite our best efforts and increased precision, it would bolster the standing of the cyclic model, for which a null result is the expected outcome.
Nature has in this way set up a decisive experiment for us, and we may very well learn the result within the next 10 to 15 years. Now, let's shift our focus to Roger Penrose's conformal cyclic cosmology. Its predictions are even more unconventional, and if they are ever confirmed, the consequences would be nothing short of astounding. Penrose asserts that events from the prior eon should have imprinted direct, observable marks upon our own universe, specifically on the map of the cosmic microwave background. But how could that be possible? According to Penrose, the principal messengers from the previous eon are supermassive black holes. You may recall that at the end of the last eon, all of its matter is destined to fall into these cosmic giants, which then undergo a slow process of evaporation through Hawking radiation. While this process stretches over googles of years, it is a finite event from the perspective of the eon itself. All the Hawking radiation emitted by a single one of these black holes eventually spreads out across the future empty cosmos. Now, let's consider this same event from the vantage point of our own eon. Through the conformal transition, that immense release of energy, which was drawn out over countless eons in the previous cycle, is compressed into a single point on the surface of our Big Bang. From our perspective, it would look as though a massive, concentrated burst of energy erupted from one spot at the very moment of creation. This energy would have superheated the plasma in that area, creating a small hotspot in what would become the cosmic microwave background. As our universe expanded, this initial hotspot would have also spread out, and today we should be able to observe it as a small, circular patch in the sky with a temperature slightly higher than the average. Penrose gave these specific anomalies the name Hawking points. But the story doesn't end there. Penrose also foresees the existence of other, even more bizarre artifacts from that time before our own. He proposes, for instance, that gravitational waves from black hole mergers in a previous cosmic age could traverse the conformal boundary, appearing in our era as concentric rings of unusually low temperature variance on the cosmic microwave background map. This isn't mere speculation. These are concrete predictions you can verify by examining the public data from the Planck satellite. This is precisely the work Penrose and his colleagues have undertaken, publishing a series of papers since 2010 where they report finding significant evidence for both these circles and the associated Hawking points. In a 2018 publication, they declared the discovery of over 20 such points with a stated confidence level of 99.98%. This assertion sent shockwaves through the cosmological community, as its confirmation would represent one of science's most profound achievements. The first direct observation of a universe preceding the Big Bang. However, the prevailing response from most cosmologists was one of deep skepticism. Numerous experts in cosmic microwave background analysis countered with papers suggesting that the anomalies Penrose identified could simply be random statistical noise within the standard cosmological framework. They took issue with his statistical methodology, arguing that in a data set as vast and messy as the cosmic microwave background, you can find almost any pattern if you search for it deliberately enough. The dispute remains unresolved today, with Penrose's team holding firm to their conclusions, while the majority of mainstream scientists find the evidence less than compelling. Yet, regardless of the final outcome, the existence of this debate is profoundly exciting.
It signifies that the inquiry into what existed before the Big Bang is no longer confined to the realm of pure philosophy. Instead, it has evolved into a field of observational science, complete with testable hypotheses. We are now presented with two starkly different cyclic models, each proposing its own unique experimental verifications. One model hinges on the non-detection of primordial gravitational waves, whereas the other involves a search for the echoes and remnants of past universes within the oldest image of our own cosmos. This situation places us at a remarkable juncture in history, an era where we might finally answer a question that has occupied humanity for thousands of years. We find ourselves at a pivotal crossroads, having journeyed from the seemingly unassailable edifice of the Big Bang theory to its emergent flaws, and from the elegant yet disquieting infinity of inflation to a renewed embrace of the ancient concept of eternal cycles. What confronts us are not merely competing theories, but two fundamentally different ways to narrate the history of our universe. Two grand cosmic stories, or, if you prefer, two cosmological myths in the most elevated scientific sense. Choosing between them is not simply a matter of selecting the right formula. It is a choice about the very nature of the universe you inhabit.
Let's first re-examine the initial narrative, a story we might title The Tale of a Singular Creation. This account begins with the standard Big Bang model, augmented by inflation. According to this version, our universe is the product of an exceedingly improbable, possibly singular occurrence. It burst forth from nothingness, a quantum fluctuation that, in its first moments, was precisely calibrated by inflation to become vast, flat, and ultimately suitable for life. While this story highlights our specialness, that uniqueness comes with a significant caveat. As we've discussed, the most logical extension of inflation leads to the idea of eternal inflation and the multiverse. Within this much larger framework, our universe's special status evaporates. It is reduced to a single infinitesimally small bubble within a boundless and perpetually churning foam of other worlds. In such a multiverse, anything that is physically possible eventually occurs. This means there are endless duplicates of you and me experiencing every conceivable variation of our existence, alongside universes governed by entirely different physical laws where stars could never form. In this reality, the principles governing our own universe are no longer fundamental. They are just the arbitrary rules that emerged from our specific cosmic lottery. Our world is not born of profound necessity, but is instead a mere statistical accident. This vision is undeniably majestic and stretches the limits of imagination. Yet it can also inspire a profound sense of disorientation and even nihilism. If all outcomes are realized somewhere, what gives our world, our principles, or our lives any particular significance? The predictive capacity of science is diminished in such a scenario, deferring instead to the anthropic principle, which states, "The universe is the way it is because if it were different, we wouldn't be here to observe it." This is the narrative of a random miracle occurring within an infinite chaos. Now, let us consider the alternative narrative, which tells a story of perpetual rebirth. This account is articulated through the language of cyclic models. Whether it's the brain collisions proposed by Steinhardt and Turok, or Roger Penrose's conformal cycles. In this framework, the universe has no definitive beginning or end. It is an eternal, self-sustaining system that progresses through an endless succession of phases of decay and renewal. The Big Bang in this context is not a one-time act of creation, but a recurring and predictable phenomenon, a kind of cosmic heartbeat. This account emphasizes regularity and order over randomness. The fundamental characteristics of our universe, like its flatness and homogeneity,
are not seen as fortunate accidents or the results of fine-tuning. They are presented as the unavoidable outcomes of physical laws operating over trillions of years, as the universe systematically cleanses and resets itself for each subsequent epoch.
Within this paradigm, the multiverse has no place. There is only a single universe, our eternal home, which perpetually transforms its state. The laws of physics regain their status as fundamental and predictive principles, rather than being a matter of chance. They are the immutable rules that orchestrate the unending cosmic dance. This narrative might appear more comforting and orderly, but it is also a far more demanding vision of reality. One theory posits the existence of exotic new dimensions, as seen in the brain model, while another compels us to fundamentally reconsider the nature of time and entropy, which is the basis of Penrose's model. Each is a tale of an eternal order masked by the apparent chaos of creation. We simply don't know which of these narratives is true, and within that uncertainty lies the entire magnificence and drama of modern fundamental science. We've arrived at a moment where our finest theories provide two completely different visions of reality, and for now, both pictures are consistent with everything we can observe. Deciding between these two possibilities is the central mission of 21st century cosmology, and this choice will not be settled by philosophers in armchairs, but on the very frontier of experimentation. The answer might emerge from future telescopes designed to scrutinize the polarization of the cosmic microwave background. If we detect primordial gravitational waves, it would serve as a powerful endorsement of inflation and the narrative of a singular creation. Conversely, their continued absence would tilt the evidence in favor of a cyclical universe. Then again, perhaps the solution is already concealed within the immense datasets gathered by the Planck satellite. It's possible that a more sophisticated analysis in the future will either confirm or conclusively rule out the existence of Hawking points, those ethereal messengers from a cosmic era long past. What does this mean for you, for people living out their short lives on a small planet orbiting an ordinary star? It means you are living in an exceptionally privileged moment in history, serving as both a witness and, in a sense, a participant in this great scientific deliberation. You are able to watch as the human mind, equipped with only mathematics and telescopes, endeavors to pose the most audacious questions imaginable. Has the universe existed for all of eternity? What preceded the beginning? And will time itself have an end? Irrespective of what the final story turns out to be, the very capacity to seek these answers fundamentally alters our place in the cosmos. We are no longer just passive occupants of the universe. We are evolving into its chroniclers and its biographers. We are striving to read the universe's autobiography, a text written in the language of light, gravity, and time. No matter how this search concludes, it is without question the most profound detective story of all time, and its next chapter is being written at this very moment.